let's solve XOR gate based on this neural network they designed. So we have x1, x2 here as input. So we have 4 neurons, x2, sorry, 4, and 1 neuron is here. So all the weight at was given previously. So after that we will get output at h1, h2, h3, h4, and we will get w0 prime here. This is the weight vector here, and we will have w1, w2, w3, w4, and so on. So now let's calculate for 1 at least. For x1 equals to -1, x2 equals to -1. So in neuron 1 we have w0 plus w1 x1 plus w2 x2. So if we calculate -2 plus -1 into -1 plus -1 into -1, so we will get 0. And for neuron 2 similarly, if we calculate based on our equation, so we get -2, and for neuron 3 w0, w1 x1, w2 x2, that will get -2, and similarly w0, w1 x1, w2 x2 will get -4. So we defined as if the sum of is greater than 0, the output is 1. If sum of is less than 0, so output is 0. So here we will get 1, you will get 0, you will get 0, you will get 0. So we are getting output of one neuron number 1, this as 1 for this -1 case. And if we combine it, let's say if we take 1, and similarly if we calculate for other inputs, we'll get similar results. So if we do, so we will have this chart. So that will be x1, x2, we will have XOR output, that is original XOR output, that we will have 4 different outputs, and we will combine it as our prediction. So we will have -1, -1. So XOR gives us 0. So here we had h1 equals to 0 and other 3 is 0. So for -1 plus 1, the XOR gives 1. So we had h2 equals to 1. So 1 minus 1, XOR gives 1, but here we had third as 1. So for 1 1 we had 0, and we are getting this. So this is possible that based on this input vector we design another, let's say this is the final layer. So this is h1, h2, h3, h4, and we'll combine this has to give result 0, this has to give result 0, this is 1, this is 1. So if we say that h1 multiplied with this weight, that will be 0, plus h2 will be multiplied with 1, h3 will multiply it with 1, and h4 multiplied with 0. This is the final output. So whenever we put h1 equals to 1 and other 3 equals to 0, so we get, so h1 equals to 1 and other 3 equals to zeros, so we'll get 0 that this XOR has. So this is correct. And similarly we have other inputs. Now similarly we will have, let's say h1 equals to 1, so this will be equals to 0. So here 1 into 1, and other thing will be 0. So we'll get 1, that is our desired outcome. Okay, so in this way we can see that this neuron is doing perfectly well. So here we have mentioned that we need a function that will take here previously, sorry, yeah, in this place we have defined a function like this one. So whenever is greater than equals to 0, we give the output at 0. Whenever we have less than 0, we give output as 0. So if we want to make it as a function, so this function looks like this. So whenever it is less than 0, we have 0, and whenever it is less greater than 0, we have 1. But this is a stiff function, so we will later see that if we use a stiff function, this is not differentiable at these 2 points. We need something smoother, so that whenever we will be calculating a differentiation for that, so we will not have any problem. So we take something like this, a function something like this, similar to this. So this function is, so this is 1, this is 0, this is the output y, this is x. So this function is called a sigmoid function. Basically a sigmoid function is this equation. So you can see that sigmoid, where is the pen, sigmoid is 1 over 1 plus e to the power minus z. So this is z. So this is the function that is given as sigma. So what this has some cool properties with it. So the property first, this is the first, less the first differentiation with respect to z will give the sigma function into 1 minus 1. You can do it ddz of this function, you will get this. So if we want to calculate the second derivative of sigma function, this is second derivative of the sigma function will give the sigma function back to itself. We don't need that now, so we'll not calculate this one. So this is important to remember. So how this function can help us, let's define that. How can we know that we are in the right direction? So we want to describe a function called loss function that will tell us how we are differ from the actual in output that we are hoping for. So loss function is defined such a way that I equals to 1 to n, that is yi minus yi squared. This is a square loss function. So thus loss function, what loss function does is that it is give a quantitative number to how far we are from this actual output that we are hoping for. This is how far we are. So as we know that loss function, this is the, let's say this is the output. We want to minimize our error. This is called error. So we want to minimize our error. So this is the loss output, let's say, yeah, this is the input vector. So we want to minimize the error so that whatever our model predicts, this is the perfect one. So in order to minimize this error, we need to differentiate this with respect to w's. So in order to differentiate this, we need to have differentiation with respect to g and f. So that's why we have taken f such a way that it is differentiable. So if we don't take sigmoid function, and we take a stiff function like this, so this is not differentiable at these 2 points. So we cannot calculate the minimum loss using that one. So we want to take a smooth function like sigmoid one to calculate this minimum. So this is the brief introduction of loss function. We will discuss loss function deeply in the next or upcoming videos. These videos are already quite long. So thank you for watching. See you in the next one.